So I'm going to talk this morning about networked markets. Okay, so in economics it's classical to think of everyone being able to trade with everyone else, but in practice there are many cases in which that's not the case. So if we think about traders in developing countries and we look at which traders are actually trading with each other, there's often family ties that govern that. And you might think that that's because there are some hold-up problems or some contractual problems in those situations, and you can't enforce an agreement. And so to reduce that scope for opportunism, you end up with people trading with their brother or with their sister and people they can trust, or people who they interact with over and over again. But this isn't a problem that's really confined to developing countries. When we look at many industries in the developed world, we also see that trade is organized on networks and that there's a network pattern to interactions. So a classic example is the garment industry in New York. So this is a very nice paper by Brian Uzi, who's a sociologist, and he went into there and he interviewed a lot of the garment manufacturers and their suppliers, and he conducted a very detailed study, and what he found is that the manufacturers would keep relying on the same small set of suppliers. They wouldn't go to the market every time and look at all the different suppliers and try and find the best price. They would keep going back to the same ones again and again. And when he delved deeper and he asked them what was going on, why do you do this, he found out that there were lots of little things it was important to have in a relationship in order for trade to be effective. So if you're a supplier to a given manufacturer, then you need to really understand that manufacturer. You need to know what it is they want when they come to you and say, I want this kind of garment or this kind of collar or and so on. If you're a manufacturer, then you need to know that your supplier can be trusted. You can go to them, you can ask them to deliver on a certain day, and they're going to be able to get that to you on that day because the fashion industry is fast moving and you can't afford to have large delays and miss your market. There are many other examples. Another classic case is fish markets. So you might think of fish markets as being almost an archetypal competitive market. So you go down to Marseille and you have all the fish vendors there with their stores and their fish, and the restaurateurs, they come along and they can go to any one of these different market stalls to buy their fish for the day. But they don't. They keep going back to the same ones again and again and again. Okay, and so there's, even in cases where we think that trade shouldn't be organized on a network, or there's no reason for it to be organized on a network, we see it occurring. Okay, and again, once you get into the details here, you can see that there may be some kind of contractual problems that a repeated relationship could be helpful for. Other good examples are Japanese manufacturers and suppliers. In financial markets, you see the same banks trading with each other again and again as well. And in fact, the network structures that we see arise here often have a certain core periphery structure. So you get a set of large banks who all trade with each other, but then there are smaller banks, and they'll often trade with just one or two core banks. And these core banks will intermediate the trade. And so a lot of the reasons we've talked about so far for the markets being networked are kind of these contractual problems or contractual incompleteness. There are also cases where there are exogenous restrictions on who can trade with who. So in the case of lawyers, you often have that you're conflicted out of representing some client because you represent one of their competitors in another matter. And that creates a network too. If we're thinking about trading natural gas, then you need a pipeline in order for two countries to trade natural gas, so we have a network again. Okay, so broadly we want to think about these kind of problems. The big questions that we're going to try and answer is, when do these markets clear efficiently? When is it that we get the right suppliers trading with the right manufacturers, the right buyers with the right sellers, the right workers with the right firms? The second thing that we're going to be interested in is, how does the network structure feed into the terms of trade that are agreed? You know, can you be in a strong position in the network and appropriate more of the gains of trade? Is there meaning to that statement? And the third thing we'll think about is that in some cases, in order to generate this relationship that you're using for trade, you really need to invest in it, either through time or maybe even more directly by building a pipeline or something like that. And an important question will be whether these investments are going to be efficient or not. And if they're not efficient, what goes wrong and when? Okay, so broadly these are the three questions we'll try and tackle. We're going to do all this in a pretty simple setup.
Just a question
yes.
about the questions.
Mm-hmm.
Your introductory example suggested that networks were offering something that anonymous markets were not. And so one natural comparison to do would be to see how a network would perform as opposed to a market where you're not establishing a long-term relationship with your traders. Is that part of this analysis?
Yes. So the question was, just for the video, what if we can compare networked markets and the kind of markets I'm talking about to a perfectly competitive market, and something that will be interesting is what's the comparison between these two things. That's something we'll certainly touch on, and we'll see as we go through. There are other questions related to that I'm not going to get to this lecture. What happens in large markets and whether we converge towards more competitive outcomes in network markets. But
is there the following question?
Please.
This is very when do two firms deal with each other, and when do they merge?
Yes. Okay. So this question is when do two firms?
Put it another way, there's a large firm using internal, since we're told that price systems the most efficient way of allocating results. Why don't large firms use price systems internally? This is close.
Right. So the question was, what about the theory of the firm world? So why can we say something about when trade is organized within a firm as opposed to through the market? And some people think of network markets as being some intermediate version of this, where you have kind of strong relationships in some cases. So I'll touch on that very slightly, but not much at all, I'm afraid. Yeah, that's a little bit beyond the scope of what we're going to talk about today. Yes.
Just a follow-up question to Professor Muskins. So in your models you will be talking to, is it equivalent between a formal market and a complete network like this?
Yeah, so that's a very good question. So the question there is, we can think of a network as being complete, where everyone can trade with everyone else. If we take that special case in the settings I'm going to give you, do we get to the competitive outcome? And broadly, the answer is going to be yes, but it's going to vary a little bit by model, and we'll see as we go through. Okay, so I'm going to try and get through 5 papers. First, all 5 of these papers fit broadly into one framework. So the framework is that we're going to have buyers that have unit demand and suppliers who have unit supply. So it's going to be a matching problem of matching a buyer to a supplier. There may or may not be investments that are needed to form the network. Some of these papers just look at a second market clearing stage, but that's fine. We can have a trivial stage there. And then after we get this network, we're going to have some trade occur and some terms of trade to be organized. And so this is broadly what we're going to do. And the first 2 papers are going to cover all the different questions. They're going to be about the investments and the trade and everything. The last 3 papers are going to be more about trade, and they're going to take a more non-cooperative bargaining approach to this. So we're going to set it up as a bargaining problem and see what we can say about the outcomes. Okay, so I can give you pictures to describe the model. So we're going to have some set of buyers on one side of the market, some set of sellers on the other side of the market, and there's going to be some potential gains from trade between these buyers and sellers. So here, this link between buyer 3 and seller 3 with an edge weight of 10 is telling us that if buyer 3 was to buy 1 unit from seller 3 or trade with seller 3, then that trade would generate a surplus of 10 between them. And they're going to have to split that 10 in some way. And we're going to assume that the payoffs of the buyer are just going to be the value of trade with the given seller. So the surplus generated less the price paid, and the utility of the seller is just going to be the price that they receive. Yes?
Should the potential gains from trade depend on what the current configuration already is? For example, if S3 is already trading with B1, B2, then maybe forming a link with B3 is not that valuable.
Yeah, so we're going to, there are lots of, so the question was what about dynamic problems? So in practice, all the examples I gave you, there's some network already in place, then we have some trade, and then there's some iteration to the network and so on. So all the models I'm going to tell you about are just going to be very simple two-stage models. I think taking that approach, we get some key ideas across, but you're right that an important direction to think more about would be a fully fledged repeated games version.
What are the stages that you're talking about?
Yes. Okay. So yeah, we'll actually, these pictures will hopefully answer that question if I've done them well. Okay. So we have these potential gains from trade. We have the buyers and the sellers. The first thing that's going to happen is there's going to be some investment stage. So the buyers and the sellers, or maybe just one of them, are going to make some investments, and that's going to actually result in trade being possible between some of them. So on a subset of these links, there's going to be investments made that's going to enable trade. On the rest of them, trade is not going to be possible because the requisite investments haven't been made. Okay, so let's suppose we get this subgraph that's formed. So now these are the buyers and sellers can actually trade with each other. And the second stage of the model is going to be thinking about how the market clears given this setup. So which buyer is actually going to trade with which seller? What are the terms that they reach going to be?
This is indivisible.
Sorry?
These are indivisible. The one unit.
Yeah, so
Don't split.
yeah, so that's a good question. The question was, are the units indivisible here? Is it really just a one-to-one matching problem, or is it unit demand and unit supply? So the answer is, because I'm assuming that utilities are linear here, so the sellers are just their utilities just the price that they receive, and the buyers is the surplus from trade less the price they receive. It doesn't matter. Generically, you're going to want to buy from a single supplier at a given set of market prices. And so you can do it either way. For simplicity, it might be best for this talk to think about it as a matching problem with indivisibilities, but it easily extends. Okay, so we get some bargaining outcomes. These dark or thick green edges represent who's trading with who. And the U1, U2, U3, V1, V2, V3 represent the buyers and sellers payoffs that they get. Okay, so we're going to have a little bit of notation. And the general approach for this lecture is going to be try to minimize on notation and get the main messages or the essences of the papers across in the simplest way possible. And I should add a caveat here that I'm going to be presenting a lot of these papers in much simpler environments than or not in the full generality that the papers give you. And if you're interested to see the full richness of the results, you should really look at the papers. Okay, so we have buyers B. We're going to match a buyer I and a seller J. That's going to generate a surplus Sij. And we're going to be thinking about matches. So a match here is a function from the set of buyers and sellers into itself, satisfying various conditions. So the first condition says that if you're a buyer, you must match either to a seller or to yourself. And matching to yourself here is shorthand for remaining unmatched. So it's just a convenient notation for doing that. If you're a seller, then you must match to a buyer or yourself. And if buyer I is matched to seller J, then seller J must be matched to buyer I. So this is a little bit wrong. This should say if mu I equals J, then J equals mu I. Is everyone happy or not? Okay, so it's a bijection. That's what's going on. Okay. Okay, so we're going to start off with the Cranton and Meinhardt paper. And in stage one, the buyers are going to simultaneously choose which sellers to link to. So each buyer chooses a subset of the sellers to link to. Each link that they form is going to cost them an amount C. And in the second stage, the market is going to clear. So this is going to be a simultaneous move first stage, and then the second stage we're going to have some market clearing. I'm going to tell you in a minute how that works, or right now. Okay, so in order to do that, we need to develop a little bit of terminology. So let's suppose that the sellers have selected some price vector P. At these prices, a set of goods is minimally over-demanded when more buyers, most preferred goods, come only from this set than there are goods in that set. Okay, and the key word here is only from this set. The second condition is that no subset of these goods is also over-demanded. Okay, so minimally over-demanded set of goods satisfies these two conditions. I'll go through an example in a minute, which will hopefully make this a little clearer. Okay, and then we're going to think about market clearing as working through an auction or through an auction algorithm. So this isn't intended literally, it's intended as a proxy for how the market might clear in a decentralized way. But the auction algorithm is going to work as following. It comes from de Morgale and Sotomayor. So initially, the seller's prices are going to be initialized to 0. At these prices, the buyers are going to identify their most preferred goods, and the price of the minimally over-demanded goods are going to be incremented. We're going to then return to step 1 and carry on, unless there is no over-demanded goods, in which case the algorithm is going to terminate. Okay, so this is just an auction algorithm. It's purely mechanical at this point. Okay, so let's go back to our example and see how this would work here. So we're going to start off with all the sellers setting prices of 0. At these prices, buyer 1's most preferred good is seller 3's good, or good 3. That gives him a surplus of 17 because he's paying a price of 0. Buyer 2's most preferred one is seller 3, and buyer 3's most preferred good is good 3 as well. So this good is over-demanded. It's minimally over-demanded, so we're going to increment the price. As we increase the price, we get to a price of 2. And at this point, buyer 1 becomes indifferent between buying from seller 3 or buying from seller 2. Both of them generate a payoff of 15 for him. Okay, and so we now have to think which goods are minimally over-demanded. And now we still have seller 3's good being minimally over-demanded here because buyer 2 and buyer 3 both uniquely demand this good. Okay, so we're going to keep increasing the price of seller 3's good. And we increase it, we get to 2.5. So as we're increasing it above 2, buyer 1 strictly prefers good 2. Nothing changes though in terms of what's minimally over-demanded, so we keep increasing the price of good 3 more until we get to the point where buyer 2 is indifferent between the two goods. Okay, so at this point, good 3 is no longer minimally over-demanded. So why is this? So both buyer 2 and buyer 3 have, it's the most preferred good for both of them, but buyer 2 also has a most preferred good that's outside of this set. Okay, and so for the same reason, seller 2's good is also not minimally over-demanded, but collectively, the goods of seller 2 and seller 3 are minimally over-demanded. There are 3 buyers whose most preferred goods come just from this set, and there's only 2 people selling these goods. So we're going to increment the price of both of these goods at the same rate. And we keep going until the price of this good gets to 5 and the price of the third good gets to 9. At this point, buyer 1 becomes indifferent between good 2 and good 1. And now there are no goods that are minimally over-demanded. And there's a way of giving everyone one of their most preferred goods. So we can give buyer 1 good 1, buyer 2 good 2, and buyer 3 good 3. Okay, so at this point the algorithm is going to terminate, and these are the prices that we're going to get. Okay, so we have these matches. Sorry?
This is like a favorite algorithm.
Sure.
So, for example, you can increase the prices, yes, and the matching will remain the same, but sellers will be better off.
Absolutely, we'll get in a minute to that. Yes? Yeah, so this is different from deferred acceptance. So deferred acceptance is something you'd use in a situation where you don't have transferable utility between these two guys. I guess mechanically it's working in a kind of similar way, but yes, it's different. Yep. Yeah, so Omer's question is whether there's always going to be a unique matching that when this algorithm stops. And the answer is no, not always, but generically there's going to be one. So if I take some surpluses and I add some noise to each, the surplus generated by each buyer and each seller, draw it from a continuous distribution, then with probability 1, there's going to be a unique matching. But not always, and in one case we'll be particularly interested in, that we'll talk about later, is where the surplus generated by any buyer and any seller generates the same amount. So it's more of an anonymous market. And that's a case in which there, it's not generic. Okay. Yes.
Are there any, for example, auction mechanism that corresponds to this matching process?
Yeah, so this is an auction mechanism, right? You can exactly imagine like the multi-unit auction where these goods are being offered and their prices, and at each, you have a given price level, everyone's telling you which good they want to buy at those price levels, and then you increment in this way.
I can imagine when there's one seller and multiple buyers, I can imagine this auction mechanism corresponding very well to the realistic auction. But in this multiple seller setting, how do the sellers coordinate to increment their prices? So I have some difficulty.
Right. Okay, good. I understand your question better now. So the question was, in practice, there's no auction mechanism like this that's really clearing a market where we have these separate sellers setting their prices. And so you're right that this is just really a proxy for how we're going to think of market clearing. And it's a bit like a Walrasian auctioneer. In practice, when we think of a Walrasian auctioneer, we don't think of an actual auctioneer standing there and raising the prices.
If the market will run in a centralized way, like with the kind of like asking buyers to point at the lowest discount instead of
Yes, but next slide. Okay, so Ben's question was, would buyers, we've assumed mechanically in this algorithm that the buyers are always choosing their most preferred goods. Do we know that's the case? Do they always want to do that? And so now let's suppose that the buyers can choose which good to point at any given point in time for any given price vector. And one of the results from the paper tells us that in this market clearing stage, there exists an efficient perfect equilibrium in which buyers bid truthfully. So the answer to Ben's question is yes, it is incentive compatible. Okay? And this is going to hold for any network structure. And so something that's nice is it's also going to hold when buyers only know their own valuations. So if I'm a buyer and I don't know, how other people value buying from these different sellers, it doesn't matter. I can still bid truthfully in this way, and I'm going to be doing as well as I could do, even if I knew all the information. Okay, and so this is one of these times when I'm not giving full justice to the paper because the paper is set in an asymmetric information world, and I haven't. Okay. So the next question that's asked in this paper is whether we get efficient investments. So let's suppose this second stage is played, so we clear the market efficiently. Are the buyers and sellers going to invest, the buyer is going to invest efficiently in forming the links to the sellers? Are we going to maximize the total surplus that's generated by the match in the second stage, less the costs of forming these links? Okay, and the result from the paper tells us that yes, there is an efficient perfect equilibrium of this two-stage game. Okay, and so this is the main result of the paper. To understand this result and the previous result, however, I want to take a bit of a detour. So we're now going to park these results for a bit. We'll come back to them, and then we'll talk about kind of the intuition for them. But now let's park this and let's move on. Okay, so the thing I want to think about is the assignment game. Okay, so we saw in this paper that, or in the auction algorithm I gave you, that really this was just a proxy for some decentralized process. And as preempted by one question, this isn't going to be the only vector of prices that clears the market. There could be other vector of prices that clears the market at which everyone is happy and doing the best they can. So to formalize that idea, we might want to look for some concept of the market being stable. Again, the concept we're going to use is pairwise stability. So we're going to look for markets, so we mean matches, who's matching to who, and utilities for the buyers and sellers, so terms of trade prices, such that there's no buyer-seller pair who leave any gains from trade on the table. Okay, so there's no buyer-seller pair that could instead do better by matching with each other. Okay, so formally, what does this mean? So an outcome in this setting is going to be some match, some payoffs for the buyers, and some payoffs for the sellers. And it's going to be pairwise stable if and only if I can take any pair, so any buyer-seller pair, and the payoffs they're getting sum to weakly more than the surplus they would generate by matching with each other. Okay, if this wasn't the case, then this buyer-seller pair could instead trade with each other and find some way of splitting the surplus they would generate that would make them both better off. In addition, we're going to have an kind of individual rationality constraint, so the utility of the buyers must be weakly positive and the utility of the sellers must be weakly positive. And the assumption, so we've normalized here the value from not trading to 0.
What is SIJ?
Yes, so SIJ is the surplus that buyer I gets when they trade with seller J. So in our graph that we saw, it's a link between I and J, the weight on the link between I and J. Any other questions?
Just to clarify, this is a possibly different solution concept than the efficient perfect equilibrium that you just described a while ago.
Yes. Yeah, so this is different from what we've seen so far, and you should think for the moment of it as just some orthogonal way to think about market clearing. Okay, so we know a lot about the structure of these kind of games, or the structure of stable outcomes. So we have a very nice paper by Shapley and Shubik that tells us an awful lot about them. So firstly, we know that an outcome is going to be pairwise stable if and only if it's robust to coalitional deviations. So we're restricting attention here to coalitions of size 2 getting together and trying to realize some profitable deviation. And what this result tells us is that if there's some larger coalition that has a profitable deviation, then there's also some smaller coalition of size 2. And kind of the very high level intuition for this is that if we had a large coalition, the way that coalition is going to generate surplus is by matching into pairs that each generate their own little bit of surplus and then splitting the total surplus generated among them. And if we can't find at least one pair that's doing better out of that and like generating more surplus than they got before, then we're not going to be able to form the profitable coalitional deviation. If that was too quick, then don't worry too much. Yeah. Okay. We also know that the set of pairwise stable outcomes in this environment is going to be non-empty. And we know that all pairwise stable matches are going to maximize the surplus that's being generated. So they're going to be efficient. And one way to see that immediately is using this link to the core. So we know if we weren't maximizing the total surplus, then there'd be a profitable deviation by the grand coalition. So, and generically, there's going to be a unique way of matching these guys to maximize the total surplus. So generically, we're going to have a unique core match, a unique pairwise stable match. But there's going to be a lot of different payoffs that are going to be possible. And these payoffs are going to have a particular structure that's going to be very nice. So these payoffs are going to form a complete lattice, partially ordered by the buyer preferences. So let me give you an example that will hopefully give you the idea. So let's suppose we have one outcome that's pairwise stable, which is a match mu, payoffs for the buyers of U1, U2, and payoffs for the sellers of V1, V2. Okay, so this is a very simple case where we just have 2 buyers and 2 sellers. And let's suppose there's another outcome that's also pairwise stable, which is a match mu. It has to be the same match because it has to maximize the surplus again, or so at least generically it's the same match. We're going to have payoffs now U1 prime, U2 prime, V1 prime, and V2 prime. Okay, because this is a complete lattice, partially ordered by these payoffs, what that tells us is that the following outcomes are also going to be pairwise stable. So we take the same match. We have payoffs for the buyers that are the max of U1, U1 prime for buyer 1, and the max of U2, U2 prime for buyer 2. And then for the sellers, we're going to take the min of these two things. Okay. So it tells us that this outcome is also pairwise stable, and the outcome where we change these maxes to mins and these mins to maxes is also pairwise stable. Okay, so in particular, this is going to tell us that there's some pairwise stable outcome that is the best pairwise stable outcome for all buyers simultaneously. And there's some pairwise stable outcome that's the best for all sellers simultaneously. Okay, and we're going to call those 2 points the buyer optimal point of the core and the seller optimal point of the core. Okay, and I'm going to switch between using core and pairwise stability because they're the same here. Okay, so let's suppose that we wanted to find the buyer optimal core outcomes. How might we do this in our example? Well, one place we can start is with buyer 1 and seller 1. So we want to give buyer 1 their highest possible payoff without them having a profitable pairwise deviation with seller 1. So a way in which we can do that is we can give seller 1 a payoff of 0. Seller 1 has no alternative here other than trading with buyer 1, so he's going to have no profitable deviation. So first of all, we need to find the match that maximizes the total surplus, and here it's buyer 1 with seller 1, buyer 2 with seller 2, and buyer 3 with seller 3. That generates a surplus of 30, and any other match here generates a lower surplus. Okay, so now we give seller 1 a payoff of 0. If seller 1 gets 0 and is trading with buyer 1, then buyer 1 is going to get a payoff of 10. And now we can think about seller 2. Seller 2 has this one alternative other than trading with buyer 2, of trading with buyer 1. That would generate a surplus of 15. Buyer 1's already getting a payoff of 10, so in order to prevent buyer 1 and seller 2 from having a profitable pairwise deviation, seller 2 is going to need to receive a payoff of at least 5. That's going to, because seller 2 is trading with buyer 2, that's going to give buyer 2 a payoff of 5. And we can now think about seller 3. So seller 3 has these two alternatives, trading with buyer 1 and or buyer 2 instead of trading with buyer 3. Trading with buyer 1 generates more surplus, it generates a surplus of 17, but that doesn't provide a very restrictive bound on seller 3's payoff. Because buyer 1's getting a payoff of 10 already, this guarantees seller 3 a payoff of at least 7. But the alternative of trading with buyer 2 guarantees seller 3 a payoff of at least 9. Okay, so that's going to be the binding alternative, and seller 3 is then going to get a payoff of 9, and buyer 3 is going to get a payoff of 1. Okay, so these are going to be the buyer optimal core outcomes. Yes?
You started with giving seller 1, 0. Can you start with giving seller 3, 0?
No, right. So I set up this example in a way that I can intuitively describe to you these payoffs by unraveling. Yeah, in general, it's not going to be possible to make these arguments.
But I guess there should be some algorithm that does the job and somehow adjusts it, right?
Exactly, and I'll tell you very briefly about that later. Okay. Okay, so what we've seen here is we get these buyer optimal core outcomes, and if you're able to remember several slides back, these are exactly the prices that were set through our algorithm that we had. Okay, and this is not by accident, this is generally going to be true. The algorithm that we had before, this multi-unit auction algorithm, is going to always terminate at the buyer optimal core outcomes. Okay. Okay, so the second piece of information that's going to be important for understanding the results we saw before is that if we go to these buyer optimal core outcomes, then at this point, the buyers are going to receive payoffs equal to their marginal contributions to total surplus. Okay. In other words, each buyer is getting a payoff that's the same increment that they're giving the market in terms of the total surplus the market achieves through its matching. Okay, so let's look at this in our market again, in our example. So here we have a total surplus of 30, but let's suppose that we were to move buyer 1. What would happen when we do that? What's the best match that we could form? Well, if we didn't do, we can't, the best match here is the same match that we have to begin with. It's going to be buyer 2 and seller 2, buyer 3 and seller 3. That's going to generate a surplus of 20. And so the total surplus before or with buyer 1 is 30, without buyer 1 is 20, and the marginal contribution is 10, which is the payoff that we saw from before, the buyer optimal payoff. Okay, we can do it for buyer 2 as well. When we remove buyer 2, the surplus generated goes down to 25. So now we want to do some rematching. So now once we remove buyer 2, we want seller 2 to rematch to buyer 1 instead. Okay, and that's going to increase the surplus we can get. But still, we're losing 5 units. That 5 units is the marginal contribution that... Sorry? Sorry, I didn't hear. Why the total surplus?
Why is it 25 when you remove this?
Okay. Right, so this guy was generating a surplus of 10, right, when we had 30. We removed him, but once we remove him, we can get to re-optimize the match. So here, the way we're going to re-optimize the match is by, instead of having seller 1 linked to buyer 1, we're going to match seller 2 to buyer 1. And when we do that, we're going to generate a surplus of 15 instead of 10 from the re-optimization. So that instead of losing 10, we're going to recover 5 of those. We're going to recover 5 units, and so we're only going to lose 5 from the surplus of 30. Okay, we'll see it again here. So here we have a total surplus of 30, matching everyone together. Now we're going to remove buyer 3. And if we just remove buyer 3 and we don't do any rematching, then we're going to lose this value, which is 10. But it's going to be optimal to rematch seller 3 to buyer 2, and then seller 2 to buyer 1. And when we do that, we have a surplus of 29, so we're only losing 1 unit in this case, which is again the buyer optimal payoff that we saw for buyer 3. Okay, so what have we seen so far? So the first thing I've tried to show you is that the multi-unit auction that we have clearing the market in this second stage is terminating at a pairwise stable outcome, and not just any pairwise stable outcome. It's terminating at this buyer optimal pairwise stable outcome. And at the buyer optimal pairwise stable outcome, all the buyers are receiving the marginal contributions that their presence in the market is making to the total surplus being generated. Okay? Okay, so now let's go back to the results and see if we have some good intuition for what's going on. Okay, so the first result that we saw is that in the market clearing stage, there exists an efficient perfect equilibrium in which the buyers are bidding truthfully. So let's suppose, so to see that this is going to be an equilibrium, let's suppose that everyone else bids truthfully, and let's think about one agent's incentives to do something different. So the first thing that we can note is that the algorithm isn't going to terminate whenever anyone else has a profitable pairwise deviation. It's not going to be a good idea for buyer I to let it terminate when they have a profitable pairwise deviation. So we're going to want to terminate it at some point where there's no profitable pairwise deviation. The best one for buyer I is going to be the one we get to anyway, the one that truthful bidding yields. Okay, so there's going to be no incentive for buyer I to deviate. The next result is that there exists an efficient perfect equilibrium of the two-stage game. So all these buyers are going to be choosing the right sellers to form links with. So again, let's suppose that everyone but I is investing efficiently. Now we know that relative to this network, buyer I gets paid their marginal contribution to total surplus. And so I is going to want to form the links that maximize the net increment in total surplus, which is exactly what the planner would want to do. And so we're going to have an equilibrium with efficient investments as well. Yes? Yeah, so I'm not actually assuming, so you're right that I haven't talked much about the investment costs, but this is for a positive investment cost of C. So you still, if you think about what the total net surplus is that the planner cares about, it's the total surplus generated by whatever match we get to, minus the amount spent on the forming the links, and it's both of these two things that figure into I's decision.
You have only this one-sided investment by buyers, and you've chosen the point so that the side that's doing the investment is getting the full surplus, and so that of course helps for efficiency, but perhaps more realistically, when both sides are investing and you're not picking out just the right equilibrium, you may not get efficiency.
Excellent. So Eric has made the very perceptive point that this model is special in a couple of ways. And one way is that we picked out this buyer optimal point in terms of the pairwise stable outcomes, and then we just had the buyers making the investments. And this isn't by accident, right? The picking out that point gave the buyers their marginal contributions to total surplus, gave them good incentives to form investments, and now we're considering just that side of the market making the investments. And Eric is very right that if we were to relax either one of these assumptions, we would get inefficiencies. We wouldn't get necessarily this efficient outcome anymore. So actually what we want to do now is we want to think about this some more. We want to explore these inefficiencies and how bad they can be. Okay, but one slide before that. So,
There's a question here.
yes, thank you.
Yeah, because I'm thinking if there is an exogenous division of surplus, then the buyer proposing deferred acceptance will get an optimal equilibrium. But here, is it this multi-unit option mechanism, is it equivalent to a buyer proposing deferred acceptance where the buyer also proposes the price? Or
So the question is this equivalent to a deferred acceptance algorithm, which is an algorithm you'd run in a world where people don't have transferable utility, so you're just choosing which object to match to, but whereas at the same time as choosing the objects, you name a price? And the answer is I don't know. So I think the closest equivalent is probably the algorithm I presented to you, but there's fundamental differences between a matching environment with transferable utility and a matching environment without transferable utility. So one important difference is in the set of pairwise stable outcomes. So here we saw that there's a unique match that's pairwise stable, generically at least. And if we go to the non-transferable utility case, we're going to get a set of matches that are pairwise stable. And actually, and interestingly, that set of pairwise stable matches is going to have a lattice structure, a little like the lattice structure that we saw on the payoffs in this case. Yes?
Coming back to the question of the investment cost.
Mhm.
So I guess it's a previous slide. So you said that the two-stage game, there is an efficient equilibrium because the incentive of the buyer to choose which investment links he wants to establish is aligned with the social pattern.
Mhm.
I guess in the two-stage, maybe I'm confused here, but in the two-stage game, the buyers pay the investment cost, the link cost, in the first stage.
Yes.
Then in the second stage, it's a sub cost for.
Mhm.
Then is that going to generate inefficiency?
So right, so the question is, because of this timing where you're sinking the investment in the first stage, the buyers are paying this cost up front, is that going to generate inefficiency? And the answer is no, but it will do as soon as we relax the model in the way that Eric was talking about, which we'll do in a minute. Okay, so this is more or less the things we've said already, so now let's go to work that tries to relax this. Okay, so let's generalize the set of outcomes that, sorry.
I have I guess equilibrium is not unique, right? So you don't have the uniqueness and the efficiency result.
Yes, that's right. So so in the previous case, there isn't necessarily a unique equilibrium. There is some of the time, and in the paper there's some results saying when, but generally there's not a unique. It's not unique.
Or maybe the non-efficient equilibrium.
So there may be inefficient equilibrium as well. Okay, so let's go to a very simple setting with one buyer and two sellers, and let's think about the outcomes that we might expect to occur when this market clears. So in this case, if we were just to think about the outcome before, this buyer optimal outcome, then buyer 1 would trade with seller 2 and get all the surplus of 15. Well, we can see that there's other payoffs that can be supported here, other splits of this surplus of 15, that would make sure that no one had a profitable pairwise deviation, also other things that are in the core. So in this case, you can characterize the set of such outcomes by one parameter, this beta parameter, and so this buyer 1 must get a payoff of at least 10 to prevent him from having a profitable deviation to seller 1, but that leaves 5 units left over that can be split in any way between the buyer and the seller. Okay, so this was a very simple case for generalizing the outcomes, but we want to be able to do this more generally for any graph. So what we're going to do is we're going to define this u lower bar I to be i's minimum core payoff. This should be a v, so we have a v lower bar j to be j's minimum core payoff. So we're thinking of I as being a buyer and j being a seller as before. And if buyer I trades with seller j, we're going to assume that each of them get these minimum core payoffs for sure. And then the remaining surplus that's left over after we've done that is going to be split according to some parameter beta. And so we think of this beta as some shorthand for the bargaining power of buyers relative to sellers. Okay, so let's go back to our example again. And let's think about this. So we can do the same exercise we did before to find the seller optimal payoffs. So here we would give buyer 3 a payoff of 0 to start with, seller 3 10, buyer 2 would then get 4, seller 2 6, buyer 1 9, seller 1 1. And something that's interesting to note that's going to be useful going forward is that this payoff of 4 is just equal to the value of this alternative match, this binding alternative match, minus the value of this other match here, this 10. So we're going to go and add 14 and subtract 10, and that's going to give us the 4. And for the 9, it's the same. To get to 9, we add 15, we subtract 10, we add 14, and we subtract 10 again. Okay, and this isn't coincidence, so why is this the case? And some of you might see it already, but okay, so let's think about buyer 2 first of all. And so this is buyer 2's minimum core payoff, right? So this is u lower bar 2. So what is that going to be equal? Well, by this lattice structure of the core, it's going to be equal to the surplus that's generated with seller 2. So let's call that S22 less seller 2's maximum core payoff. Because when the buyers get their minimum core payoff, the sellers are going to get their maximum core payoff. But we know what seller 2's maximum core payoff is. It's going to be seller 2's marginal contribution to total surplus. So how did we find that? Well, we removed seller 2 from the graph, and we saw what rematching we did to optimize it. So when we remove seller 2 from the graph, we lose 10. So we get minus S22. But then we get this link instead, because B2 is going to rematch to seller 3. So we get plus S23, and then we lose S33. And if you combine those two equations, you're going to find out that buyer 2's minimum core payoff is just going to be this 14 minus the 10, and we do the same exercise for buyer 1. Okay. We can do the same thing for sellers, and now I have on this picture the minimum core payoffs for all the buyers and all the sellers, and we can now split the remaining surplus according to this parameter beta, and here we get a range of different possible outcomes. So formally the convex combination of the buyer optimal point of the core and the seller optimal point of the core. So why is this useful? Well, we're going to want to think about the incentives to invest in links, and now I can write down the payoff of buyer 1 just as a weighted sum, where the weights are this beta and 1 minus beta, of the different links in the network. So it tells me exactly how the different links are affecting the payoffs. And so something that you get immediately from this that's nice is that buyer 1's payoff doesn't depend on his link to seller 3. So the most valuable link in the network doesn't affect buyer one's payoff here, or any of these outcomes. And so if one immediate observation is that buyer one wouldn't invest money in forming the link to seller three. It's not going to change their payoff. Conditional on forming the other links, there's no incentive to form that link as well. Okay, and just to show you the link between buyer 1 and seller 3 was the 17 link that didn't appear. Okay, so something that, so far everything's been hopefully kind of straightforward, but there's a potential problem with this, with doing this. So in order to find these kind of chains that are going to tell us how much each buyer values each link in the network, we might end up with a different chain for each buyer, and these chains may have no relationship to each other. And so we could end up with some very complicated network decomposition when we get to larger graphs. So here it's convenient that when we think about buyer 1 rematching, they rematch to seller 2, and then when buyer 2 becomes a match, they rematch to seller, buyer 2 becomes unmatched and they rematch to seller 3, and that's the same person that buyer 2 was going to match to when we directly removed seller 2 from the graph. It turns out that this is always the case. So the key technical result from this, or a key technical result from this paper shows you that you can always do this. And that's going to mean that there's a nice simple representation of which links matter on a given network, and is helpful for thinking about the investment incentives that we'll turn to now. Okay, so both of these questions I think have been preempted at various points. But now we have these more general payoffs. What might go wrong? So generally, you might think that the buyers and sellers could have an incentive to form links that they don't really want to match over, because those links are going to improve their minimum core payoff, and that's going to translate into their actual payoff. And so they might have an incentive to overinvest in outside options. So we might get overinvestment for that reason. Alternatively, well, there's another type of inefficiency that might occur, and that comes from a hold-up problem. It could be the case that it's very efficient to form a link between one buyer and a given seller, but if the buyer is going to appropriate all the gains from trade from doing so, the seller's not going to be willing to invest in that link. And so we might get underinvestment for that reason. Okay, so a question we might want to answer is, how important are these inefficiencies? Are they small in some sense? Can they be large? And ideally, when are they large and when are they small? Okay, so let's think about two-sided investment first. So we're going to now have the buyers paying an amount gamma c and the sellers paying an amount 1 minus gamma c to form a link. And now, because we have both buyers and sellers paying these investment costs, we could have coordination problems that would mean that the empty network is always in equilibrium. And so we're going to refine the Nash equilibria using pairwise stability that you've seen already. Okay, so the first result says that as long as gamma isn't equal to beta, so the cost share of the buyer is equal to their bargaining power, there are potential match surpluses such that all the gains from trade are going to be lost to underinvestment on all stable networks. The second result says that there can be overinvestment. You can lose some surplus, but you can bound how much, and it's never more than 50%. And in fact, you can find the function bounding, and it looks like this. So at its worst, it's 50%, but often it's considerably less than that. Now, if we're worried about this underinvestment problem, it's really being driven by this gamma not equaling beta. But what if the buyer and the seller could get together and change the gamma? They could make some agreement where, you're going to benefit more from this link, so you should pay more towards it, and I should pay a little bit less. So let's think about what happens when we allow that. And when we allow that to happen, now we find that overinvestment becomes the problem. So for all levels of bargaining power, there exists some potential match surpluses such that all the gains from trade are lost to overinvestment on all stable networks. So again, you're losing everything that you might be able to get. But now it's because of overinvestment, but there's no underinvestment anymore. Okay, so which kind of inefficiency you're going to get is going to depend on how you think about these networks being formed. Okay, so there are some limitations to this. Two that lead on nicely onto the thing we're going to talk about now is that this market clearing has been quite reduced form so far. And you might think that in practice we're talking about small numbers and buyers and sellers, so really they're going to be bargaining with each other in some way, and we might want to model that explicitly and look at the non-cooperative game and see whether there are any games that generate these outcomes as equilibria, and whether we perhaps start to get inefficiencies once we allow for people to interact strategically with one another in terms of making offers and rejecting offers and so on. Okay. Okay, so the first paper we're going to think about that does this is going to be a paper by Coriomenes-Bosch. Here we're going to have the surpluses of 1 or 0. So we're now in this world where we don't have these different gains from trade. And what's going to happen in this model is that one side of the market is going to post a price at once. Those prices are going to be accepted or rejected by the other side of the market, and then we're going to move on to the next stage and carry on. So we're going to have a discount factor delta. The results are going to be for delta going to 1, and we're going to be looking at perfect equilibrium. Okay, so the protocol is going to be that the buyers are going to be selected to be the proposers with probability p, and the sellers are going to be selected to be the proposers with probability 1 minus p. The proposers, whoever they are, so either it's all buyers or all sellers, they are simultaneously going to post prices. And then the responders, the other side of the market, are simultaneously going to either choose a price that they accept or they're going to reject all prices. A proposer is going to be matched to a responder only if they have a link and I accept that price. And when multiple responders accept the same price, we're going to implement the maximal match that we can. Once I and J are matched, they're going to exit the market. They have these agreed upon terms of trade, and they leave, and then we continue. Okay, so let me give you an example of what this might look like. So let's go back to our case we've been looking at, or let's go back to this case where we have now unit surpluses and all the links. And let's suppose that we start off with sellers being selected to be the proposers, and let's suppose they name these prices. So seller 3 is here demanding a price of 1, seller 2 1/2, and seller 1 3/4. And the buyers now get to choose whether there's a price that they want to accept or whether to reject them all. So let's suppose buyer 1 and buyer 2 reject everything, and buyer 3 accepts the price of 1. So in that case, these guys become matched. In the next round, let's suppose the buyers are selected to name a price. Let's suppose the buyers name 0.9 and 0. Seller 1 rejects. Seller 2 names 0.9, so they're willing to accept that price. They match, and there's nothing more we can do now, so now we end. Okay, so I should emphasize this is nothing like equilibrium play, but this is just an example of the protocol. Okay, and in this outcome, these would be the payoffs of the different buyers and sellers. Okay, so when we're thinking about this problem, a first thing to think about is whether there are some links there where agreement could never be reached. Okay, so if you look at this graph, if there are a pair of buyer and sellers who, if you think that link was selected, they wouldn't reach agreement with each other. Yeah, excellent. So the B1 and S3 was the thought, and that's exactly right. It should look to you, hopefully intuitive, that S3 is in a strong position here. They have B2 and B3 that have to trade with them, and B1 is in a strong position here. They have S1 and S2 that has to trade with B1. And so because this buyer and this seller are in strong positions, they are going to end up getting payoffs, limit payoffs that are greater than 1/2. Because they have limit payoffs greater than 1/2, they're not going to want to trade with each other. So this link is not going to be used, and it is not going to be used. If we look at this case, we can do the same kind of exercise. This is a little bit more subtle, but again, seller 2 here is going to be in a strong position and is not going to want to trade with buyer 1, who is also in a relatively strong position, not quite as strong as before, but still strong enough to prevent trade being profitable. Okay, and in this case, it's going to turn out that these two links are the redundant links that are not used. So it can get more complicated, but the general idea is that some people, even ignoring certain links, are going to be getting limit payoffs that are sufficiently high that they don't want to trade with someone else. Okay, and what we can then do is remove those links from the graph, think about the graph without those links, and it's going to be then relatively easier to see what payoffs we're going to get. Okay, so how do we find these links in general to remove? And the answer is we use the Edmonds-Gallai structure theorem. So what we're going to do is we're going to partition the nodes into three types. We're going to start off with the C types, who are going to be our weakest type. And they're going to be those who are unmatched in at least one maximal matching. So there's going to be some way to get the maximum number of matchings that are possible in a graph without involving these agents. We're then going to have a type A, who are going to be the strongest types. And these agents are going to have a link to a C agent. So they're going to be linked to a weak player. And then everyone else we're going to label B. Okay, so doing this, you can show, or it's shown by Edmonds and Gallai, that in every maximal matching, if I is in the set A, then I ends up matching to someone in the set C. And in every maximal matching, if I is in the set B, then I ends up matching to someone in the set B. And so that implies, when we're going back to our network, that there are certain links where agreement is never going to be reached. We're not going to ever reach agreement between two people in the set A, or someone in the set A and someone in the set B. So two strong people, or one strong person and one even person, as long as the bargaining is going to result in a maximal matching. So we can go to our network, we can remove these links, and after we've removed these links, we're going to be left with three kind of components in the graph. We're going to have those where there are fewer buyers than sellers. We're going to call those the GB components. Those components with fewer sellers than buyers, they're going to be called the GS graphs, and those components with equal numbers of sellers and buyers. Okay, so let's see how this decomposition is going to work for the examples that we've seen. Okay, so here the highest number of matches we can get is 2. So there's no way to get 3 sellers and 3 buyers all linked. And there are therefore maximal matchings in which seller 1 is unmatched, seller 2 is unmatched, buyer 2 is unmatched, and buyer 3 is unmatched. Okay, so these are going to be type Cs. As these are type Cs, we then look for agents who have a link to them. So buyer 1 and seller 3 both have links to them. They're type A. And there's no one left over, so in this case there's no type Bs. And then we can remove the edges between the strong types, between the type As. And we get down to the network that's going to be relevant for this problem. Okay, we can do the same thing here. Here the type Cs are B2, B3. That makes S2 a type A, and B1 and S2 are type Bs. So we remove that link because it's from a strong to a medium player. Same thing in this case, and we get down to this. Okay, so the result from this paper tells us that there exists a perfect equilibrium in which, in all components that are of the type GB, buyers get a limit payoff of 1, and sellers get a limit payoff of 0. In all components that are type GS, sellers get limit payoffs of 1 and buyers get limit payoffs of 0. And in the GE components, they get limit payoffs of P and 1 minus P. Okay, and so these outcomes are actually a lot like the competitive outcomes that we've seen before, or the pairwise stable outcomes, and they actually correspond to the same ones that we saw in the previous case, but with this P equal to the bargaining power beta. An important difference is that in this case, we had to have surpluses equal to 1 or 0. We had these simple graphs instead of the weighted graphs. Okay. Okay, so the next paper I want to talk about is a very nice paper by Mihai Mânia. And in it, we're going to again stick with having surpluses that are 1 or 0. But now, what we're going to do is once a buyer and a seller match and exit the market, they're going to be replaced by replica agents. So someone's going to come in that has exactly the same network position as the people who left. And that's going to allow the market to be stationary. And that's going to make our life much easier than it would otherwise be, as it's going to make our life easier. And again, we're going to look for perfect equilibrium. Okay, so what exactly is the protocol? So first of all, we're going to select a link at random in this graph. Once we've selected the link, the two agents on either end of the link, one of them is going to be the proposer, one's going to be the responder. It's going to be equal probability which assignments we do. The proposer is then going to make an offer to the responder, and the responder is going to accept it or reject it. If the responder rejects it, we're going to just move to the next round and nothing changes. If it's accepted, that pair exit the market with agreed upon terms, but are then replaced by replica agents. Okay, so what does this look like? Let's suppose that the protocol selects this link, then selects buyer 1 to be the proposer. Buyer 1 proposes a split of a half-half with seller 2, and let's suppose seller 2 rejects that. Now the protocol happens to select the link between buyer 2 and seller 2, selects buyer 2 to be the proposer. He asks for a quarter and to give seller 2 3/4, and let's suppose that's accepted. They exit the market, but then before the start of the next round, there are replica agents that come in that take their place, and then bargaining looks the same as before going forward. Okay, so this is the model we want to think about, but in order to think about it, it's going to be helpful to go back to a bargaining model that many of you will know. So we're going to think about there being just one buyer, just one seller. The size of the pie is going to be 1. Buyer is going to propose with probability P, seller is going to propose with probability Q, and then we know there's a unique perfect equilibrium. And we know that in that, and that the limit payoffs of the buyer and the seller are proportional to their relative probability with which they're selected to be the proposer. Okay, so let's call these payoffs the Rubinstein payoffs. So it's the payoffs you get from one buyer and one seller bargaining with each other in isolation, given that they move with probability P and probability Q, or they're the proposer with probability P and probability Q. Okay, so now that's the aside done with. We'll move back to Mihai's paper, but we're going to think about a very simple case in which there's one buyer and one seller. So this case is exactly the same as the simple Rubinstein model we saw. We select this link for sure, so it doesn't matter, and then we select each person with probability half, so it's like that case with P equal to Q. And so what would we expect in this case to be the limit payoffs of the buyer and the seller? Well, we'd expect them to be a half a half. So that's okay, but what about now? What about when we have one buyer and 3 sellers? So if we think about what's the probability that in any given round buyer 1 is the proposer, well, each of these links is selected with a probability 1/3, and each time one of these links is selected, buyer 1 is going to be the proposer with probability 1/2. So he's going to be the proposer with probability 1/2, and each of these sellers are going to be the proposer with a probability 1/6. From the perspective of buyer 1, it doesn't matter which of these links is selected. All the sellers are identical to him. And so from buyer 1's perspective, it's as if he's bargaining with a single seller, but that seller only moves with probability 1/6, and he moves with probability 1/2. If you're the seller, it's much the same. You have to wait until your link is selected. When your link is selected, you're the proposer with probability 1/2. But in between, the buyer is going to be able to move many times, and so is going to be much more patient than you. And so this model is going to be equivalent, or is going to be as if there's one buyer and one seller. The seller moves with a probability of 6, and this seller is representative of all the different sellers in the market. And there's one buyer representing the buyer who moves with probability of 1/2. And they get there. If we apply our formula that we saw a couple of slides ago, we're going to get limit payoffs for the buyer of 3/4 and limit payoffs for the seller of 1/4. So no, not really in this paper. So there's there's another paper I'm not covering in this lecture where they with Elliott, where they consider different protocols and they compare them both. The other protocol is a protocol in which you select players first, and then either they get to choose or they don't get to choose who to make an offer to. And I think the case he makes in that paper is that they're both kind of reasonable proxies, but in different situations. So if we're walking around at random and bumping into people, maybe this is quite good. Whereas if it's more deliberate and we're looking at the market and we're kind of thinking, right, I want to negotiate with this person and we're choosing who to, then maybe another protocol is better. Okay, so it would be nice if we were done and that's the way we could just solve this bargaining model, but it's not going to be that simple. So let's suppose that we have this graph and we try to do the same thing again. So now if we were to think about this link, what agreement buyer 1 would reach with seller 1, well, with these proposer probabilities, we might think that seller 1 is going to get a payoff of 1/4 and buyer 1 will get a payoff of 3/4. By symmetry, if we do the same between buyer 3 and seller 3, we might expect limit payoffs to be 1/4 and 3/4, but then if we were to select the link between buyer 1 and seller 3 and again do the same exercise, they'd only get limit payoffs of 1/2 each. And so you can start to see they wouldn't want to reach agreement with each other and they'd do better ignoring the link. So let's look for an equilibrium in which they do ignore that link and they always delay when that link is selected, but otherwise it's like we saw before. Okay, so if we do that and we remove that link, it's now as if these are the new proposer probabilities for everyone. And now when we do the exercise, it works again. So we get buyer 1 getting a limit payoff of 2/3, seller 1 getting a limit payoff of 1/3, seller 2 getting a limit payoff of 1/3, and so on. The important thing is that the limit payoffs of buyer 1 and seller 3, ignoring this link, together sum to more than 1. And because they sum to more than 1, as the players become patient, it's never going to be worthwhile them agreeing on this link when it's selected. Okay, so we can remove this link from the graph, and then we'll be able to do the exercise in that subgraph. Okay, so the link that we deleted in that example is the same link we saw deleted in the Edmonds-Galai decomposition. So can we just apply that again and get the same results? Well, it's not quite that simple. So it is true that we can never reach agreements over these links, but this isn't going to be quite enough. Okay, so it's sometimes going to be enough. In this case, if we applied Edmonds-Galai, we'd get the right answer. In this case, if we applied Edmonds-Galai, we'd get the right answer as well. But in this case, we wouldn't. So let's see what would happen in this case. So let's do the Edmonds-Galai decomposition again. So who are the payoffs that are not involved in a maximal match? Well, here all the buyers fall into this set. Right? There's a maximal match in which any of these buyers is excluded. That makes them the type C weak players, and that makes the sellers both strong players. So in this world, there'd be no links to delete. There's no links between strong players or strong medium players. Okay, so if we don't delete any links and we look at the probabilities with which everyone moves, and we get these probabilities, and the problem is, so there's a couple of problems, but this link is one problem. Right, so here, buyer 4 moves with a probability of 6 and seller 1 moves with a probability of 1/3, but seller 1 would rather be trading with these guys who move less frequently. They only move with a probability of 12. And so the way you would get an equilibrium here is you'd remove that link, and then everything works again. And so these are the right limit payoffs for Mihai's model. But and so we need to be deleting links in addition to the links deleted by the Edmonds-Galai decomposition. Yes.
How do they agree to erase the link? Because if you think about bargaining in infinite series, even if delta is close to 1, you have an infinite series where you could erase the link. You have
Yeah, okay, good. So the question is, how do they erase the link? And this is where I haven't been careful enough in explaining what I mean. So when we're erasing the link, I'm thinking about it being as if the link is erased. And what I really mean is they're playing strategies such that when that link is selected, they delay. They don't reach agreement.
but that happens after an infinite time, right?
So
They are doing this
R- Yes, but it's right. The different people are coming in. The new replicas are coming in. They're facing the same bargaining situation as everyone who came before them, and they have the same strategies. They have these strategies that are again going to be to ignore these links that we're deleting. Okay. Okay, so in the paper, there's the fully fledged algorithm that really does this properly. You should take a look at it. It's going to delete a superset of the links deleted by the Edmonds-Galai decomposition. And after these decomposition payoffs are going to be determined by the ratio of buyers to sellers on different sides of the markets, as we've been seeing. Okay, so what's going on here is, well, what do we get as a message out of this paper? Well, there are these alternative bargaining opportunities, and these alternative options allow people to be more patient or less patient. When I have more opportunities, I'm effectively more patient because I'm bumping into people I can reach agreement with more often. And we know from the intuition of a simple Rubinstein model that being more patient is going to lead me to get a higher share of the surplus. A key thing is that it's only these credible alternatives that matter. So there are some links that aren't, the agreement's never going to be reached over, and those don't affect my bargaining power. The stationarity assumption that we're making here to get tractability, it's very strong. It's hard to think of small markets in which it's realistic to have replica agents come in and replace those who've just left. But if we have a large market and we're thinking of a steady state, we have flows of buyers and sellers into the market, it can be more, you can get the model to work in just the way that we've seen. And so it seems like a good model for large markets and perhaps a less good model for thin, small markets. The final thing to note is that it's hard to think about efficiency or at least mismatch in this kind of setting. So if I wanted to maximize the kind of flow of surplus being generated, then every time I selected a link, I'd want two players to reach agreement on it. But that perhaps doesn't seem like the right measure of efficiency, and it's at least not getting at this problem of mismatch. Maybe there are pairs of agents we don't want to match because it's not the maximal matching for this given set of players who are currently available. So in order to think about the efficiency question, which I think is important, we're going to want to have a model where players are exiting the market. We don't have the stationarity that's here, and we want to see if we can say anything in that case. Okay, and that's the last paper. Okay, so we're going to move back now to a world where different pairs of agents generate different surpluses. There's going to be no replication after exit, and there's going to be a set of active agents at any given point in time, who are the players who haven't yet reached an agreement and exited the market. We're going to have a discount factor as before, but now the solution concept we're going to use is Markov perfect equilibria instead of just perfect equilibria. And I think I have a slide in a minute, but the Markov state is going to be the set of players who are active. So what does this mean? It means that when we're thinking about the strategies of the different agents, they can condition on the set of active players, but not on any richer part of the history of the game. Sorry?
Does the complete history of the past agreement matter for the action?
Yeah, so I think another way of interpreting this question is there a difference between the Markov perfect equilibrium and the perfect equilibrium? If we were allowed to condition our strategies on the full history, would we get different answers? And the answer is yes. So in this setting that I'm about to show you, I don't have a folk theorem or something like that tells you can always reach an efficient agreement, but there are related settings in which we know that is the case. And in the examples I'm going to show you, there exists an efficient perfect equilibrium, as well as the Markov perfect equilibrium we'll focus on. And if I get time, which I'm not going to get, then we can talk about the selection. And there are experiments that go to the lab and try and look to see whether which equilibrium is selected and what's going on. whether we get the inefficiencies that are predicted by the Markov perfect equilibrium or not. And the punchline is it's even worse than predicted. But okay, so we're going to select a proposer to be the proposer with probability pi. They're going to choose who to make an offer to. The offer is going to be accepted or rejected. If rejected, we're going to move to the next round, and if accepted, then they're going to match, they're going to exit the market, and we'll go to the next round. So in pictures, suppose buyer 1 is selected first to be the proposer. They choose to make an offer to seller 2. That offer is 10 for them and 5 for seller 2. Suppose seller 2 accepts that offer, then they exit the market. Then in the next round, we bargain with this network. Okay, so Markov perfection is going to do a couple of useful things for us. So the first thing is it's going to tell us that you're going to accept, each player is going to accept any offer better than their continuation value. So for each player, we're going to have continuation values that depend just on the set of active players. And you know that if you reject an offer, the set of active players isn't going to change. So you know you're going to get your continuation value. That means that you're only going to be willing to accept payoffs higher than that. If the proposer chooses to make, and we also know that if you're the proposer, you're going to do one of the two things. You're either going to offer someone just the amount that they need to accept, their continuation value, or else you're going to make, you're going to delay. You're not going to make an acceptable offer. Okay, you can show that a Markov perfect equilibrium exists here. The setting isn't so standard because you have these max operators and the value functions because you have to choose which player to offer to. But nevertheless, the proof technique is very similar to other results. So there's not much to be gained. Okay, we're going to say that an equilibrium is efficient if it results in the match that maximizes total surplus. Okay, so one thing that this does is it permits me to call an equilibrium efficient even if there's some delay that goes on before we reach the efficient match. That's going to turn out not to matter for one main reason, and that's because there's going to be an equilibrium, no delay without mismatch. Okay, so you could change the definition to not permit delay and it's not going to make a difference. It also seems that it might be appropriate because the results are going to be for high delta, so the cost of delay is likely to be small. Okay, so let's go through one example and then we'll stop. So here we have 4 players. The efficient, so we're going to vary the value of this link y, the surplus that can be generated between A and D, and all players are going to propose with equal probability. So if we start with a value of y that's less than 100, then there's a unique Markov perfect equilibrium in which everyone proposes efficiently. So for y less than 100, the efficient match is AB and CD. Okay, so these arrows with a 1 means that A proposes with probability 1 to B. Why is that going to be an equilibrium? Well, if these players are doing it, it's as if they're bargaining just with each other. It's as if they're bargaining bilaterally. What pairs are they going to get? They're going to get their Rubinstein payoffs that we saw before. So they're going to get 50 each here. If they get 50 each, then A's getting 50, D's getting 50, and there's going to be no profitable deviation when D's selected to be the proposer to instead offer to A, because he has to give A 50, and the surplus Y is less than 100, so there's going to be less than 50 left for him. Okay. However, as we increase the value of this link Y above 100 but less than 143, then that's no longer going to be an equilibrium. If everyone behaved like I was saying, that's still always offering just to their efficient partners, they'd still get these payoffs of 50, and if they got payoffs of 50, then they'd have a profitable deal. A would have a profitable deviation to instead offer 50 to the other and take the remaining amount themselves. So that's not an equilibrium. What is an equilibrium is for A and D to mix, to sometimes make efficient offers, and to sometimes offer to each other, which is inefficient. So why is this an equilibrium? Well, whenever they offer to each other and reach agreement, we get the inefficient match, and C and B, are left unmatched and get a surplus of a payoff of 0. So by increasing the frequency with which A and D offer to each other, they push down the continuation values of C and B to the point where they're indifferent. And as we increase the value of Y, they have to make offers to each other more and more frequently to push down this continuation values of these other two players more and more, so it's equally profitable to make the two offers. And as we get to 144, so when it's less than 200, it's still efficient for C to match to D and A to match to B. But now we reach the corner solution in which A always offers to D and D always offers to A. Okay, so now with a probability of half, we're going to get the inefficient match. We're going to get A matching to D, rather than A matching to B and D matching to C. Okay, so you can generalize the insights from this example into a theorem. You can show that an efficient Markov perfect equilibrium exists for all delta close to 1 if these Rubinstein payoffs, which are defined by just bargaining bilaterally with your efficient match, so the payoffs you'd get from doing that, are in the core, so they yield no profitable pairwise deviation. And only if these payoffs belong to the core. So whenever this condition isn't satisfied, there doesn't exist an efficient Markov perfect equilibrium and we have inefficiency. Okay, so by allowing players to exit the market and the market being non-stationary, we start to see inefficiencies cropping up, and we can start to be worried about whether we're getting the right people matched to the right firms, or in other markets, the right manufacturers, the right suppliers, and so on. Okay, and there are some experiments to do this, but I'm going to stop here because I'm out of time. Okay, thanks.